So remember the last class? So we're basically discussing about the basic principles behind remote sensing. Now we'll continue with that. Uh, this is where we left, if you remember, no? It's about the
Yes, sir.
deleterious factors of cloud cover. Are you able to hear me?
Yes, sir. Yes, sir. We can hear you.
Okay. So there are certain aspects we'll be discussing about the atmospheric effect of uh, effects of scattering. I mean, effects of atmospheric scattering. One is you have direct sunlight coming from sun, and then so the basically what you get uh, on the ground is the direct sunlight and diffused skylight. So these are the two things which you get on the ground, which in fact again get through the atmosphere back to the sensor. And upcoming radiation, this is light reflected upward from terrain feature, backscattered light from atmospheric particles. The overall result is a reduced image contrast, and infrared photographs shadows completely dark as no scattering for this range of uh, wavelength. In infrared, you don't have any in that range. You don't have much of scattering. So in thermal infrared, haze is less pronounced. Microwaves are immune to haze and penetrate clouds, right? So you have more scattering. I mean, selective scattering. What we say we discussed is the Rayleigh scattering, which lesser the wavelength, much higher the scattering, and that is so blue light is scattered much more than in comparison to the red, right? Now we'll just all of you are aware how it happens. I mean, you have incident light, and then part of the energy, say incident energy. Let's say light is a form of energy, so part of it get absorbed, and whatever gets absorbed, a part of it also get transmitted back by as emission, and a majority of it get reflected as reflected energy, right? Now, reflection, as we know, is a surface phenomenon. So, the amount of reflection depends upon the surface smoothness, orientation of there is the angle of incidence and angle of reflection, right? Now, uh, it is angle of incidence is equal to angle of reflection. So, and earth surface is not a smooth one, so you have varied different facets of earth surface are at different angle to the incident light, and light also the direction of light varies from time to time in the entire day. So eventually the reflection is depends upon the surface smoothness, orientation of the object, which is the reflector, and polarization of the light. As I told you in last class, light gets polarized in two perpendicular direction. I mean, if you consider the light to consist of uh, some quantas particle, they vibrate perpendicular to the direction of light. So that is how they make a sine wave. So a light energy can also get polarized into two perpendicular vibrating directions. Those things we'll be discussing in detail when we take up the microwave remote sensing and wavelength of radiation, of course. So what is specular reflection? It's basically uh, it's a mirror like. I mean, whatever comes gets into the energy, total energy that gets incident is completely reflected back, right? Diffuse reflection is basically because surfaces are not, no surface is specular. Specular means it's a completely flat surface, right? So there, whatever energy get incident, no, it get completely reflected in the visible range, of course. But no surface is a even smooth surface. So every surface has a large amount of irregularity. So depending upon that, um, there is a diffuse reflection. Whereas in case of microwave, that is in 1 millimeter to, let's say, 1 meter, there is more specular reflection. See, like because if you have a larger wavelength or long wavelength radio range, rocky terrain may appear to be smooth to the incident energy. In visible portion, even the fine sand particles appear rough, right? Because the lesser the wavelength, wave, that energy of that particular wavelength will be interacting with the particle. No? So if a sand will appear rough to a visible spectra, contrary to a microwave light, which is microwave energy, which is having a much larger wavelength, right? So this is specular reflection. You have a very smooth surface, and the angle of incidence is equal to, you can draw a perpendicular right to the perpendicular to the specular reflector, and the incident angle is equal to reflect angle of reflection. On the contrary, so if you have a source of light like this, and all these particles that you see, no, they they face the source of light in different angle. As you could see, light fall here, light also fall here. So if you draw a perpendicular here, the angle of incident and the angle of reflection, so the reflected light will go in this way. So depending upon the varied phases, varied uh, uh, reflecting surface, you can say, the position of the reflecting surface with respect to the incident light, since in a rough surface it is quite varied, so in total you have a diffused reflection. Is it understood? Okay. Now coming to what exactly is a spectral reflectance curve. uh, have you heard of it? What is a reflectance curve? Now I'll show you this. So let's say in the x-axis I have the wavelength of light, and y-axis I have the percentage of reflectance. Right now, the amount of light that gets reflected from different material. Let's say we're having a particular pixel, right? In that pixel we are having ground pixel. Let me say we are having vegetation here, right? Now vegetation has minimal reflection, let's say 10%, 5% reflection. I mean, the amount of light that come, almost 95% get absorbed and 5% get reflected back. Is it understood? It has a small peak, maybe 8 to 10% uh, get reflected back. Rest of the energy get absorbed in the visual sector by the vegetation, right? Then it has a huge, deep, you can say, this absorption in the rate range of EMR. So almost 95% get absorbed and 5% get reflected, right? So this is basically reflectance curve. Now, in case of near infrared, almost 50% of the light energy that comes in near infrared range get absorbed, and rest 50% get reflected. So this is what a spectral reflectance curve is. Are you able to get me?
Yes, sir.
Okay. On the contrary, this is a water body, right? So suppose you are having a water body in a particular ground pixel. Ground pixel means the equivalent, I mean, how much area one particular pixel is covering on ground, right? Now, water, as you know, absorbs almost 90% of the total energy that comes into it, right? So it barely reflects.
Yes, sir.
Yes? Hello? Excuse me? Are you able to hear me?
Yes, sir.
Yes, sir.
Yes, sir. We can hear you,
Yes,
sir.
sir.
Water is an ideal observer, right? There again, in the infrared range, it absorbs, suppose you have total light, almost 100% of the light energy in infrared range get absorbed by water. It has some amount of reflection in the blue, green, and less in red. And in NIR, the whole energy is absorbed. So water is an ideal observer, right? And this is of course the bare earth, right? So these are the spectral reflectance curve which you should have a basic idea about. And whenever you are going for interpretation of satellite data, no, this idea about the spectral reflectance curve helps you to do quantitative analysis, right? Then again, this is a generalized spectral reflectance curve. See, there can be a difference also, like different kind of trees, no, have different chlorophyll content, right? So a tree will again, you have a small peak. See, the total out of the total energy that is coming from sun, almost 95%, 100% is absorbed in the blue range. Almost 98% is absorbed. 95% is absorbed in the green range. Again, almost 97% is absorbed in the red range. And here again, 60% is absorbed. So this is the spectral reflectance curve of deciduous tree, right? Whereas in conifer, the amount of light get absorbed in NIR range is almost 70%. Could you make out? So, in general, the near infrared has higher reflection in NIR range, and like this, see, you can make a distinction between coniferous tree and deciduous tree if you have data about NIR. Like these are the different kind of trees and their spectral reflectance in near infrared range. So if you have NIR image, I can make a distinction between these different kind of trees. Like here you see, you have a panchromatic image of a forest area. The panchromatic image has energy level from zero point 0.4 to zero point 0.7, right? Now here you are not able to distinguish, make any difference between. Here basically all the trees they look similar, right? Now let's say I have a infrared photograph, right, of the same area where the energy level that has been measured is zero point 0.7 to zero point 0.9, which is basically near infrared range, right? As you could see, the deciduous tree has more infrared reflectance in comparison to conifer. This is a grayscale image. Higher the reflectance, higher the brighter is the color, right? I mean, it is in a grayscale image, so white represent a. Uh, now, of course, these are not trees, right? These are not trees, so you can discount this. But amongst the vegetation, you can discount these areas based on their shape and all that. But these are the trees, right? Now, amongst the trees, if you see the deciduous trees, like here, they have higher reflectance in the infrared range, as we saw in the uh, as we saw here, right? This has higher reflectance in the NIR range. So when I make a NIR image in a grayscale, the deciduous trees looks brighter in comparison to the conifers, right? So these are how it is dependent. I mean, why the vegetation uh, has a higher reflectance in air. Now, this is a spectral reflectance curve of healthy vegetation. You have right from zero point 0.1 to 14 micrometer. So, as you could see, vegetation looks green because it has a small peak at green, right? All said and done, almost 90% of the total energy that comes in visible range is absorbed, right? But then again, in the green range, it has a small peak. It reflects more green energy in comparison to blue and red, right? Blue and red energy, the energy in blue and red range is basically absorption for photosynthesis, right? Okay. Now, in this range, the NIR it has a higher reflection because of the cell structure, right? And whatever free water is there, no, uh, they they are responsible for a huge amount of absorption in this 1.8 micrometer range and around 2.2 micrometer range absorption by free water in plant tissues. So this can also be taken into account for deciphering the he- health of a vegetation. If you compare a healthy vegetation spectral curve with, because this curve is for a particular pixel. Is it understood? Each pixel will have different. Let's say I'm having 10 bands, so each pixel will have one DN value for each pixel. For each pixel will have one DN value for a particular band. No, suppose I have 10 bands, right, or 15 bands. I have a blue band. That particular pixel will have some DN value for blue. The same pixel will have a DN value for green. So same pixel will have a DN value for red. Same pixel will have a DN value for NIR. Same pixel will have a DN value for this absorption. So depending upon how many bands I will have that many pixels, right? So spectral reflectance curve of soil, it is dependent on many factors, no such thing as typical soil reflectance. It depends upon the particle size distribution, soil color, organic matter content, moisture content, presence of carbonate, iron oxide, surface crust, salinity. So based on these are some of the idealized reflectance curve of five mineral in soil, organic dominated. This is organic dominant, right? Then B is minimally altered. Minimally altered means you don't have much of clay mineral development. C is again iron. You have a lot of iron alteration. D is, so these are different spectral curves for different kind of material. And then, as we were discussing, no, you have let's say the ocean water A, right? As you could see at NIR range, no, near infrared, beyond NIR, everything is getting absorbed, right? It has a higher reflection in blue and green, then gradually it reduces. Whereas in turbid water, this is very good, very useful for coastal area study, for deltaic study. So for turbid water, we'll have lot of particles in it. Am I correct?
Yes, yes.
Hello.
Yes, sir.
So turbid water will have a lot of particles in it. So you will have a somewhat higher reflectance even in blue, green, and red range in comparison to a normal ocean water, right? Normal ocean water is A. Whereas if you have a lot of chlorophyll, no, water with chlorophyll, then there will be a increase. Let us see. You will have in NIR, you will have a much relatively higher reflectance curve, reflectance in the NIR range also, because chlorophyll accounts for, uh, I mean, chlorophyll is basically vegetation, right? So suppose you have a lot of algae in the water, so algae, musk, those kind of things, if you have in water, no, so there won't be complete absorption in this range, NIR range. There will be relatively higher reflection. Relatively, see, in fact, almost 95% of 98% of the energy is being absorbed, right? So, in total, if you see in water, nowhere you have more than 90%. Almost 90% of the incoming solar radiation is absorbed in both in visible and near NIR range. In infrared range, it is all everything 100% is absorbed, right? So, as we discussed, absorption depends upon the composition, thickness, and wavelength. An object may be highly absorptive in the visual band, but completely transparent in infrared region. Absorption of electromagnetic radiation leads to rise in temperature of the material. These are some of the different rock or mineral and their spectral reflectance curve, right? Now see, these are all absorption which are typical of this material. And this absorption area, if you have a band here, then you will be able to quantify how much hematite is there. You can quantify how much pigeonite is there. So these absorption bands helps you identify different rock material as well as mineral as well as the vegetation and other things, right? Now, this will take up subsequently hyperspectral scanning and all that. I will, with this, I will end this and we'll move over to the other topic, that is sensors and platforms, right? Now, anything you would like to ask? Anything you would like to ask?
No, sir.
No, sir.
I mean, everything is understood?
Yes, sir.
Sir.
It's a very unlikely situation anyway. Yes?
It's understood, sir.
Okay. And now we'll go over to is it visible, the presentation?
Yes, sir.
Okay. Now we'll go to see to do remote sensing. You require two things. One is sensor. A sensor is basically the uh, instrument which measure the amount of energy. Understood? And then you require a platform on which the sensor can be fitted, right? The platform could be an aircraft or could be a satellite, right? So these are the two things which are required. One is a sensor, another is a platform, right? Now a remote sensor has the ability, something similar to your rods and cones in the eyes, right? It has the ability to measure electromagnetic energy in different wavelength bands, right? So for each band, it will have a particular energy level which it measures, or let's say it takes the entire energy and then measures. Suppose the entire energy fall on a sensor. What it does, it is convert that energy into different energy level of different bands. How much energy has come in blue band, how much energy has come in green band, how much energy has come in zero point 0.6 to zero point 0.7, how much energy has come in zero point 0.7 to zero point 0.9. So sensor has that capability, right? And measurements made by sensors attached to a static moving platform, static or moving platform. Yes, sorry. Static or moving platform. So then we'll discuss. I mean, the charge coupled devices. What I was telling you, no, they are basically the energy measuring element, the CCD, charge coupled devices, right, or solid state detector. They are equivalent to your rods and cones, right? Then the sensor is a combination because the light has to be routed through one optics, right? It could be a lens, it could be a combination of lens and a mirror. So in a optical remote sensing, light is routed through a lens, either only a lens or through a lens and a combination of mirrors, right? Then eventually it falls on the detector, right? And then instrument is a combination of sensor plus electronics. I mean, electronic devices, they basically uh, what it does is the detector measure the energy which goes through some optical lens and a combination of mirror. Then you have the whole lot of electronic instrument which convert this signal a into a measurable quantity. I mean, the energy that is generated on a, because light energy when it falls on a detector, it creates an electrical energy. That electrical energy is scaled into a scaled or amplified depending upon the kind of satellite that you have or sensor you have. Uh, there are a combination of factors, uh, combination of mechanism which uh, changes and which make those energy levels into a quantity, into a what we say the process is basically known as quantization. It convert those electrical signal into a scale, right? That scale could be 0 to 255, it could be 0 to 1025, depending upon the binary system, that is the radiometric resolution of the sensor, right? So you have the detector, the sensor. Sensor is detector plus optics, and instrument is sensor plus electronics, and you have the platform. The platform can be ground platform, it can be air, or it can be space. Ground platform means you can keep a sensor and try to, like something your airport radars are. They are basically ground platform, right? You have a platform on board which you have the microwave detector, so they can tell you how far the plane is, and which and they can of course give signal to the plane in which direction it should go. So those are the ground based platform. You can also have air based platform like aerial aerial image acquisition. You can have light detection and ranging, that is through aircraft, and of course you can have space-based platform which is known as satellite. Right now, ground measurements could be handheld or could be fixed platform. As I discussed in case of radar, you can have handheld platform also, where in defense people uses this handheld platform where they can detect any incoming microwave signal that has come. And airborne, of course, you have balloon, you have aircraft, You have unmanned aerial vehicle. Of course, you have drone, right? And spaceborne platform. Now, for all practical purpose, you now will be discussing about the spaceborne platform, right? Now, before I get into the platform, how the do you have any idea about orbits? Hello, hello.
Yes, sir.
What is the shape of Earth orbit?
Okay.
It's oval, no?
Yes, it's oval.
It's oval.
Well,
And then it is what is the orientation of Earth equatorial plane with this orbit? Or let me say we, is it popping? Let's say the Earth pole, Earth axis of the Earth is at what angle inclined to this orbital plane?
it's very easy.
Yes. Is it perpendicular?
No, sir. Only 10, 23 something.
Okay. Yeah, tell me. 67 degree, no? 67 and a half. Okay. And then, what about Earth own satellite? I mean, Earth has a satellite, no?
Yes, sir.
Yes, sir.
Moon.
The moon.
Yes. So how it moves? Okay.
Surrounding the Earth.
It moves around the Earth, isn't it? Right?
Yes, sir.
So for all practical purpose, uh, the moon is a natural satellite, right? Okay. So it moves around the Earth, right? And its orbit, it has an orbit, no?
Yes, sir.
Okay. So, or if you want to put a satellite around the Earth, now how to put say you have to define the orbit first, right? The selection of orbit depends upon what kind of data you want to acquire, right?
Yes.
You can
Yes, sir.
have orbit along the equator. You can have orbit along the moving and a satellite moving around the pole. You can have an inclined orbit, right? And how much time the satellite will take to complete one complete revolution around the Earth, right? And of
Yes, sir.
course, the inclination angle, the angle between the path of the satellite and the equatorial plane, right? Now, now orbit could be circular, uh, it could be low Earth orbit. I mean, to the tune of uh, let's say 100 kilometer to 3 to 400 kilometer, or it could be near Earth orbit. Most satellite are here. Low Earth orbit are basically on the top of the atmosphere, just near the top of the atmosphere. Here, of course, you have several spy satellite and all that. They are all low Earth orbit, and near Earth orbit are mostly remote sensing satellite, right? Remote sensing Earth observation satellite. Uh, these can have a height range of 300 to 6,400 kilometer, and then of course you have very satellite which can see the entire Earth at one go. At least half of it can see. They are basically uh, those kind of satellite when you need a satellite always looking at India. You require that kind of satellite also, no?
Yes, sir.
Okay.
For
Can
telecommunication.
anybody? Yes.
For telecommunication or
Yeah. For telecommunication. Yes.
or
tell me.
any channel.
Yeah,
मतलब
for
system-
local cloud estimation, right?
Yes.
So satellite can be polar or near polar. Normally, remote sensing satellite are near polar. It's not exactly polar, right? Now, it has different satellite have. It has an inclination of, let's say, if you consider from around 10 degree, it makes an inclination of around 10 degree with the axis of the Earth, right? And the satellite normally a remote sensing satellite is normally made to pass over a particular area or over a particular latitude at the same local time, right? So that it can collect good data. Normally in the morning, remote sensing satellite are near polar in nature, so it descend the Earth and then ascend the Earth on the other side, right? Is it understood?
Yes, sir.
And when it descend the Earth, when it is in descending node, it it is daytime, right? Is it followed? When it descend the Earth in that particular part of the Earth, it has to be day. Okay. And when it ascend, no, when it goes up from South Pole to North Pole, it will be night on the other side, no? Are you able to get me?
Yes,
Yes,
sir.
sir.
Yes,
So
sir.
it has a descending node, it has an ascending node, and since the next time when it descend, no, the Earth must have moved a bit to east. Yes,
Yes,
agreed.
sir. Yes, sir.
So that way it goes on collecting data continuously and collect data at the same local time from. So it has it passes equatorial pass is normally between 6 a.m. to around 10 a.m., right? That is the time of pass of all the remote sensing satellite at the equator, right? Now, these are all sun synchronous. Sun synchronous, as we discussed, no? Okay. We'll be discussing about the sun synchronous again later. Now, there is something called geosynchronous. Now, geosynchronous satellite is a satellite which has an orbital period of one sidereal day. You know what is a sidereal day? Can anyone tell me? A day, how a day is defined? A day is
So,
defined by one complete revolution of the Earth around its axis. Agreed?
yes, sir.
Yes, sir.
A sidereal day is so here the internal. So you are considering one complete revolution around its own axis when judged from the Earth itself. No, yes. Now suppose somebody is looking at the Earth from a distant star, right? So in reference to a external framework, no external frame. Suppose somebody is sitting on a distant star, while Earth make one complete revolution around its own axis and come back to the same. Let's say India, and let's say particular your own uh, Nazrul University. Somebody is looking at your university, right? Somebody looking at your university.
कचरा करा देगा ना?
Excuse me.
बे, आवाज नहीं आ रहा यहाँ.
आवाज नहीं आ रहा है? Hello.
यस सर आवाज आ रहा है
अभी आ रहा है?
यस सर
हाँ सर आप सर
What I was telling is, let's say somebody is sitting on a distant star, right? Okay,
Yes, sir.
and looking with a radio telescope to Nazrul University, and Earth is revolving, no?
Yes.
And by the time, uh, so gradually the Nazrul University go away, and again it will come back to him, no, to his telescope, right?
Yes, sir.
By the time it comes back, how much time it will go? Will it be 24 hours?
No, sir. 23 hours, 15 minutes, 56 minutes, 4 seconds.
The reason is, you are aware of the reason because the Earth must have moved a bit along its own orbit, right?
Yes,
Right.
sir. Yes,
So
sir.
that is what is known as sidereal day, and geosynchronous satellite has a orbital period of one sidereal day, right? It could be circular to non-circular orbits. Inclination with equator could be 0 to 23 degree, right? They are normally uh, equatorial, either equatorial or they have orbit which are inclined to equator at an angle of 23, maximum at an angle of 23. So they are basically needed for communication, right? Now, a geostationary satellite is primarily a variety of geosynchronous satellite which has inclination with equator. It is equatorial orbital plane, right? Its orbital plane is same as the equatorial plane, right? And it can view 45% of the globe approximately, right? It is stationary with respect to a part of the earth. Like insert, always look at India, right? India and adjoining area, or Asian subcontinent, and the whole of it, right? So it is so placed that it can always look at Indian subcontinent. Is it understood?
Yes, sir.
yes sir
So this is what I was telling you about the sun synchronous satellite. It means that the orbital plane of the satellite recessed around the Earth at the same regular angular rate at which the Earth moved around the sun. The angular velocity of the orbital plane of the satellite is synchronized with the Earth's movement around the sun. This characteristic caused by the satellite cause the satellite to cross the equator at the same local time 9:30 to 10 a.m. At places it can vary also. This is in case of Landsat. In some of the satellite, even 6:30, 7 o'clock also you have the crossing time of equator, right? This is equator, but then again you can have, say suppose West Bengal, it may be crossing around 8 o'clock, right? Understood?
Yes, sir.
So normally the equatorial crossing time is around 9 to 10, right? Okay. So to be this, it has to be a polar or near polar orbit, but remote sensing satellite are normally near polar. If it is only polar, you won't be able to gather information about the complete Earth, right? There will be the overlap will be more at the polar part. So we'll come to those things again. So the ground track. So this is what I was telling you about. As the Earth, these are the ground track of the satellite on a projected Earth, right? As you could see, this is the descending node, right? And this is the ascending node. Okay. So this dotted line is on the back side. So when you descend like this side is dark, no, and ascend like this. So while it ascend also, it gather data, particularly in normal thermal data can be acquired even if it is night, no. So You have nighttime data of in the thermal range. So the visible optical sensors are normally switched off when the orbit when the satellite ascend. Okay, this is the strange satellite ground tracking system, and you have this is the Landsat ground track, right? It starts from here. One, two, three, four.
Yes, sir.
Yeah, tell me. Landsat normally here it crosses the equator at 12:30. Landsat at 9:42 local time. Yes. Here 12:30 p.m. the pole it crosses. As you could see, there is a 15th track. It's not coinciding. So there is a gap between the first track and the 15th track, right? So these are the what is known as swath. I mean, how much area it covers. Like Landsat covers approximately a width of 185 kilometer, right? The entire this is known as swath. So first day one, right? Then this is orbit one, day one, orbit two, day one, right? So day two again, this is 15 or 15th orbit, right? Day two, this is 16th orbit. So this is how the entire Earth it goes on collecting data, right? Because there will be an overlap, no? So it goes on collecting data from the entire Earth. Okay. So this is a meteorological satellite, Meteosat, uh, which can see half of the globe, right? Now, coming to sensors, sensors are designed in such a manner that it depends. I mean, what kind of sensor, what kind of studies you are going to do. Suppose you are going to do land-based studies, then you should have sensors in a particular range of EMR, which will help you uh, to because land is full of rock and soil and vegetation, right? Land is all about rock, soil, and vegetation, isn't it? So you should have these are the naturally occurring material: rock, soil, vegetation, and of course the glacier. So you should have sensors which are capable of discriminating and gathering information about this naturally occurring material. You can also have suppose water, like if you there is something called ocean sat, and then in Indian satellite you have ocean color monitor, which has three. Because if you want to study exclusively water, then you should have at least 3 to 4 bands in the blue green range, because otherwise in the NIR range water in any case it won't show you any reflection, right? And suppose you want to do study of atmosphere, you should have uh, bands or bands which are capable of gathering information about clouds. Like you should have bands around 1.4 range, so that you know how much cloud is there, right? And of course, it is also classified based on whether the sensors are active or passive sensors, right? Active sensors are basically the sensors which send its own, which has its own source of energy. Normally, microwave sensors could be active. Even infrared sensors could also be active. Like you have the light detection and ranging leader. They are not satellite remote sensing. They are basically airborne remote sensing, where you send a light signal normally in infrared range and then measure the signal back and get an idea of how distant the object is from the moving aircraft, right? That is how a digital elevation model is made. Or it could be a passive sensor which just measures how much energy has come, where the where the source is also uh, passive, that is sun's electromagnetic radiation. External source of energy, passive sensors, 1 picometer to 1 meter EM spectrum, gamma ray spectrometer, amount of gamma ray emitted by upper soil. See, these are all, but again, these are more of a geophysical data. I mean, gamma ray spectrometry, which is done by aircraft, airborne geophysical survey, is all about, it is more of a geophysical survey. These are not covered under the remote sensing. Uh, Here it is not a reflection process, it's a natural decay of radioactive decay of material. That is, then of course you have the field spectrometer, non-imaging variant of multispectral scanner, imaging spectrometer, where you can collect data by taking a spectrometer to field and measure how much energy has come. You can also have a camera, aircraft, shuttle, spy satellite. All of you are aware about stereo photography. Hello.
Yes, sir.
All of you know what is a stereo photography is?
Yes, sir.
Then these are all passive sensors. A video camera. This here the source of energy is the sun's electromagnetic radiation. Visible colors. You can have visible color. You can have low cost. This is basically a low cost solution for qualitative purposes. These are all qualitative purpose, because in this you cannot do any kind of measurement, right? They are not metric camera, right? To have a metric camera where measurement can be done accurately, we should have a aerial camera. Uh, they in fact can give you fairly accurate measurement on the photograph. And then of course you have the multispectral scanner. You have imaging spectrometer, you have thermal infrared scanner, you have microwave radiometer and scanner. These are all passive scanners, whereas the active sensor, as I was discussing about the airborne laser beam, a radar altimeter. Any example can you give about a radar altimetry in satellite remote sensing? Have you dealt with any digital elevation model? How-
Yes, sir. We're starting now.
Okay, how can you have a digital elevation model? Are you aware of it?
No, sir.
There are three ways to have a digital elevation model, or four ways, let's say, right? One is you take a dumpy level. You know dumpy level.
Yes, sir.
Take a dumpy level. Know the you have a benchmark, Survey of India benchmark. You know the RL of that particular benchmark, and then you go on measuring the height of different places, right? You have a digital elevation model, right? By ground survey, right? Then then you can have a aerial camera, take photograph of the same area from two different position on the sky, right? So you have a stereo pair, right? As
Yes,
you
sir.
know, we are able to see in three dimension because we have two eyes, isn't it?
Yes, sir.
Each eye generate a image of the same area, no? Or same area, same person, same object, isn't it? Each of our eye generate image of the object that you are seeing, right? So the same object is being viewed from two different angles throughout two eyes, right? That gets fused to form a 3D model, right? That is what stereoscopy is all about. If you have two images of the same area taken from two different perspectives, you can build a stereo model, right? Okay. The other way is you send an aircraft and put uh, infrared beam to the surface, measure the time taken by it to go back to the aircraft, and then measure the distance. You know the speed of the light, you can compute. That is light detection and ranging, right? Okay. So
Okay, sir.
you send a signal, receive back the signal, you compute the time taken and measure the distance. That is how a digital elevation, digital terrain model can be made. Other thing is, if you have a satellite, you can send a microwave, because laser beam won't reach this far. No, you have to send a microwave, right? Microwave signal or radar, what you say, it comes, touch the ground and go back. So that is what a radar altimetry is about, right? Radar altimeter, right? One of the best example of radar altimetry is subtle radar topography mission, right? All of you have heard of SRTM?
Yes, sir.
Okay. So active sensors are basically imaging radar, 1 millimeter. Sorry, this is 1 millimeter to 1 millimeter to 100 centimeter domain. 1 to 100 centimeter domain. You have K, X, C, S, L. These are all this nomenclature all developed during Second World War, as I have discussed, and these are uh, the backscattered energy is measured. I mean, you send a signal in some range of either K, X, C, S, L, or P band, and receive back the signal. Radar reflection is basically backscattered. It depends upon the surface structure, surface roughness, and moisture content. So this is the way you can compute the surface structure. You can have an idea about the surface roughness. You can have an idea about the moisture content, right? So based on these, the categorization of the sensors, you can have passive sensors, that is gamma ray spectrometry, multispectral scanner, imaging spectrometry, field spectrometer, photograph, video. You have thermal scanner, you have passive microwave radiometer. This can be, you can also have a passive microwave radiometer. You can have a radar altimeter, you can have imaging radar, you can have laser scanner in infrared range, right? These are the active sensors. Now, as we discussed, sensors can be airborne. Airborne sensors are normally expensive because you have to plan a mission and you have to execute it. Whereas the spaceborne sensors, there are many Landsat 5, 7, 8, that is operational land imager. You have the SPOT, you have the Indian remote sensing satellite, and many such satellite. Uh, you have Aqua, you have Terra, right? There are all of you have got yourself registered in Earth Data. Hello,
Yes.
have you all registered yourself with Earth Data and USGS?
Yes,
So
sir.
Bhuvan sir, registered in a Bhuvan or USGS.
Get yourself registered with Earth Data also. Earth Data is
Yes,
basically uh, NASA site. You can create a login in Earth Data. It has some of the, uh, I mean, it has linked to USGS also. If you don't get the data that you require here, you can get it from there also. So Bhuvan, of course, you have a lot of finished product like land use, land cover, and but high resolution data. Many of the high resolution data, because Bhuvan only share the least three data, right? Now, Earth data
Yes, sir.
login, you can get many declassified data of old, I mean 1970s, 80s data also you can get, Sentinel data and some of the declassified defense data also. If it is available about the India, you can get. So if you are doing some kind of uh, historical study, of a particular area, you can have a good lot of data in Earth Data login. So please create a login in Earth Data. If you find any difficulty, we can discuss in subsequent classes, right? Now we'll just, for an example, we'll be discussing about Earth Landsat 7. Of course, Landsat 8 is now it provides some of the best quality data that we'll discuss subsequently. Uh, Now, as we see, Earth observation you want. This is one platform. So you have odd view. These are the very high resolution data, right? You have odd view 3. It's a multispectral odd view 3. You have 1 meter resolution. You have quick bird, 1 meter spatial resolution, and then these are the high resolution. These are the high resolution data. Spin, IRS, Panchromatic. You have 6.5 meters spatial resolution. And then as we see here, these are the Landsat like Landsat Pan, Resourcesat, Landsat Thematic Mapper, Landsat OLI. They are all around 30 meters spatial resolution, right? IRS LIS 3, LIS 4 is of course 6.5, and JRS and SIR, European satellite, French satellite, RadarSat. So these are all. So this is just to show you the different resolution, and of course, if you have higher spatial resolution, your swath also will be relatively less, right? Like QuickBird, it has a swath of hardly 30 kilometer, right? On the contrary, a Landsat TM has 185 kilometer swath. This, of course, we were discussing last class also. Image is basically a raster image is an array of number where data is organized in grid and column, usually represent geographic data. So you have so finally, if you zoom it up, it is basically rows and columns. Each pixel has a unique number, has one unique number for a particular band of satellite, right? Now, suppose a satellite has 10 band, each pixel will have 10 different DN number. Is it understood?
Yes, sir.
Yes, sir.
So, unlike a vector system where the in a vector image, the 0, 0 normally starts from bottom left. In a raster system, it starts from the top left, right? This is the first 0, 0 pixel. This is then x-axis. You have 0, 1, 0, 2. Like this is how you address the pixel in a raster, right? So this is the whole process of remote sensing. Like you have the satellite passing over the Earth, maybe around this particular place, maybe around 10 o'clock, and you have a sensor over here. The light gets reflected in different direction depending upon the object, the material. So we are discussing about only one pixel here, right? And then of course you let's say you are having 1 million pixel, finally image is made. But here let's say this particular point, and this will have finally only this energy reaches, not everything reaches the satellite. The This particular energy reaches the satellite. What it does is it takes the energy and then convert it to an electrical energy, and then electrical energy, sorry, it creates an electrical impulse. This energy level that goes, it's basically electromagnetic radiation, no? It creates an electrical impulse, right? And that is converted into a digital number in different bands. There are two ways. I mean, this radiation, when it goes from here, it can be, you in childhood, you must have played with what we say, a kind of diffraction of light, no? Diffraction of light into various color of light. Remember, in a prism, if you pass the light through a prism, it gets separated into different wavelength of light, no? And do you remember?
Yes, sir.
Yeah, there are certain mechanism like this also in the sensor. The energy that comes is segregated into different bands depending upon how many bands are there in the satellite, and then the electrical energy is converted into uh, this is the electrical energy, which is finally converted into a digital number based on the radiometric resolution of the sensor, right? If it is an 8-bit, it will be from 0 to 255, where 0 represent the minimum amount of energy, 255 represent the maximum amount of energy, right?
Yes, sir.
And then of course you get a, based on these, let's say I have 5 bands. For each pixel I will have 5 values, and then I'll take only 3 band and make a false color composite, right? Assign a blue, green, red colored gun to 3 digital number, and each pixel will have 3 digital number. And if I assign the color gun, 3 color gun to 3 different bands, I'll get a FCC, right?
Yes, sir.
Yeah, resulting images are made of reads of pixel. Sorry. Each pixel store a digital number measured by the sensor for a particular band, right? So if you have 8 band, there will be 8 digital number in a pixel, right? Represent individual areas scanned by the sensor. The smaller the pixel, the easier is to see the details, right? Now swath is basically the area covered by the satellite, or yeah, this is how it is going, no? Okay.
Yes, sir.
Now, digital image data format, this is how, as we were discussing, no? If you have, they are basically known as, this is a 8-bit quantization. So, 0 represent the least amount of energy, 255 represent the highest amount of energy. Now, you have an array of numbers. So, let's say you are having 4 bands, you have 4 array of numbers, and the okay, I think this has already been discussed. So once you have an array of numbers, you can see a panchromatic image. If it is a single band, then if you have more than 2 or more bands, you can see what you do basically is, yeah, this is a discrete data. So there is a difference between discrete and continuous data, right? Here, there is no categorization of the data. Can you see? Here, this is a multispectral data, and contrary to this is a thematic image, right? Deal with categorical information about an area used and created by analytical operation, used to extract information about multispectral images. Let's say the red represent forest, this represent built up area, this represent water body, this represents something else, this represents fallow land. So this is a classification. This is all discrete data. Whereas continuous image, yeah, you can see uh, each band can be seen in a grayscale, and you will have a grayscale image where the dark represent the lowest amount of energy level and the brightest represent the highest amount of energy level. And only three bands can be seen simultaneously by assigning color gun. Now this is a Landsat image. Landsat band 2, when it is assigned a blue color, band 3 is assigned a green color, and band 4 is incidentally the NIR band in case of Landsat. So when you assign a red color gun to NIR band, in fact the vegetation, since it has the highest reflection signature in red, it looks red. On the contrary, you can also have a 354 RGB BGR combination. Band 3 assigned a blue, 5 assigned green, and 4 assigned red. The urban area gets highlighted in this particular band combination in case of Landsat 7. And of course, this is a true color composite of 1, 2, and 3 assigned blue, green, and red color gun, right? Pyramid layers, you must have, you are doing GIS, no? So anytime you put a raster in the window, it asks you to whether you want to build a pyramid layer, right? Pyramid layers are basically a short file in which what it does is suppose I have four. Say here how many number I am having? I have a 16 digital number. The same 16 can be converted into 4 and can be converted into 1, right? So this is not your raster remains same. Your raster could be 1 million by 1 million or 1000 by 1000. What it does, it has it made say the original image is by a code. When you open the complete image in your viewer, no, it shows you only this part, this image it shows you. As you go on zooming it shows you. So this won't be possible unless you have a pyramid layer assigned to that particular raster, right? So this is in nutshell for this. You have different band combination in Landsat, 432 RGB, 321 RGB, and 453 RGB. There are many such combination possible, which highlight certain aspect of the Earth observation. Now, next will be coming to multispectral scanning. Now, multispectral scanners scan the Earth's surface. It's storing the data in storing the measurement as pixel, measurement for different EM ranges, and scanning can be done by electromechanically or by electronically. Right? There can be two different kinds of sensor. One is electromechanical sensor with a moving mirror or electronically, right? Now, I'll show you how I think this solid. See, then how the sensors are normally planned. Uh, Advantage of scanning is basically the entire optical domain is covered. It can also cover the thermal domain. Some of the scanners like Landsat 8, even Landsat 7 also has thermal scanners. And you get a band setting and band widths are more flexible, large dynamic range. You have a digital output. Now, coming little bit to discuss about the solid state detector, as I was telling you about the charge coupled devices, the electromagnetic radiation measured by electro-optical device called solid state detector. What it does is it basically take count of how many photon, right? So detectors basically count the number of photons, how many photons are, and then it convert into a radiance. Radiance means it creates the number of photons that hit a optical heat a electro-optical devices eventually generate a electrical current, right? Now that is measured as watt or milliwatt per square meter, how much area, from how much area it has come, how much area on the surface of the earth it has come, through which solid angle, that is known as steradian. Steradian is basically a solid angle. You know radian is a measure of angle. Pi radian is 180 degree, right? Remember? Hello?
Yes, sir.
Yeah. Steradian is basically the
Yes, sir.
solid angle. The cone. If you angle is a two-dimensional, no? Steradian is a three-dimensional. I mean, any energy that goes from surface, no, it goes through a solid angle, right? So this it so radiance is basically measured in watt per square meter per steradian, and this is converted into a digital number. The radiance is converted into digital number, where depending upon this is not the process is known as quantization, and depending upon the radiometric resolution, it can vary from 0 to 255, or if it is 9 bit, 10 bit. So it is basically 2 to the power 8, right? 8 bit quantization means 2 to the power 8. So that many levels of energy can be measured, right? Now, as we discussed, no, what is the spectral, what is the response of a solid state detector? Like now, if a detector is capable of measuring EMR in the range of 550 to, it is measuring at 800 also. Some energy it is measuring, no? Right? Understood? So its
Yes, sir.
effective range is from here to here. Is it followed? Effective range is not from here to here. Effective range is from half minima, from 50, from here, no? From 560, 70, 575.575 to, these are nanometer, right? To 705 maybe, right? So this is the effective range, normalized spectral function. So if this is the eventual curve of spectral response, then the width of the band is taken from here to here, right? Okay. Now we'll just I'll try to show you how uh, there are two kind of sensing. One is uh, across the track, one other is along the track, right? Across the track, what happens? You have a,
Sir, आवाज कट रहा है सर.
yeah, tell me. Tell me, come again. Hello.
Yes, sir. अब आवाज आ रही है.
Am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So there are two kinds of multispectral scanning system. One is across the track, cross track, what they say, and another is along the track, right? Cross track is basically sweep, right? What it does is you have very few detectors, right? Like suppose for band one I have one detector, band two I have one. So for each band I have only one detector. What it does is it starts swinging from this to this, from here to here it starts swinging and cover this entire area. This 185 kilometer swath of the of Landsat, no, it is covered by one detector by just swinging like this, forward, backward, forward, backward. The scanner also will be descending. This sensor will be descending, no? So it goes on scanning line in a. So on the contrary, if I have a, these are all linear imaging. For each band I have scanning sensor, right? So at one go I will be covering the entire track, right? Then go to the next track. So it covers the entire swath line by line. Can you see here what is happened? You have a, this is the ground track, this or swath, right? This is the ground track, this is the swath. In case of Landsat or whisk broom scanner, what they say, it you have a detector here and a rotating mirror here, right? And the detector measure this ground cell, then come here, then measure this, then come here, then measure this, and this moves, right? And instantaneously it sends the signal to it goes to detector. I mean, this rotating mirror helps look at the ground cell in different way and cover the entire scan line. You require less of detector. Area that is, and the instantaneous field of view is basically when the detector looks at one ground cell, right? So this is how you have a ground cell, you have a rotating scan mirror, and you have a motor which rotates and then a detector, right? So it goes on like this. It measure like it goes from here to here. Okay. At the same time, this is going down, let's say, right? Then the next line, so it covers like in this fashion. One comes back without taking any data and then goes, right? The disadvantage is since you have straight line appears to be curved, right? So FOV, the field of view is very large and it leads to geometric distortion. So that they can be systematically corrected. See, this is a normal straight line on the surface of Earth. It appears to be curved, right? So there are, since the parameters of all this motion is known, so those correction can be applied and you eventually get a restored image only. You don't get this original distorted image, right? So these are the sigmoid curvature problem and geometrical distortion which takes place in case of a it looks like a rectangle. A square may looks like a rectangle. A straight line looks sigmoid. A circle or ellipse looks like something bulged up at the center, right? So uh, all Landsat satellite are Landsat 7 up to 7. They're all whisk-broom scanner. And here, as we discussed, no, scene overlap varies from it. This happens in all. Scene overlap varies. It is the minimum at equator and maximum as we go towards the pole. One of the major difference between the whisk-broom channel or disadvantage you can say is the dwell time. How much time the detector stays on a particular ground pixel. It is less in comparison to the linear imaging sensor, right? The amount of time, because it has to cover the entire line by swinging the mirror, no? So it has less time to record the data, right? So the energy level recorded often become less, right? Okay. On the contrary, this is a linear detector array. So you have a field of view, and each CCD will subtend an angle here. This is known as instantaneous field of view, right? So here, as you could see, it scanned line by line. So there is less geometric distortion since there is no moving parts, and the dwelling time of the detector on the ground pixel is more. So, and then of course you have a side scanning system. Side scanning systems are normally the radar system where you have side looking radar. So this is just a comparison of dwell time. Dwell time of the detector upon a ground cell is 1 into 10 to the power minus second per cell, whereas in case of a linear imaging, it is 5 into 10 to the power minus 2. So that is the difference. So with here, the since the dwell time is less, you need a really high, uh, what should I say, very powerful detector to capable of measuring the entire energy that comes. Whereas here, less powerful detector can also measure since the dwell time is more. Okay, I think that is. So we'll end with this. If you want to ask something, we can discuss. Or else we'll stop here. The next class, of course, I'll let you know subsequently. Okay.
Thank you, sir.
Okay. Bye.
Okay, sir.
Mhm.